so we've got quite a large consortium there, as well as local partners to the research university, so local community colleges and other small colleges. And the idea behind this diversity, which you can see captured in the table at the bottom, is we really want to design a curriculum that works for a broad swath of students from the ground up. And so we think, well, I'll say technically how we're planning to do that a bit more in a moment, but obviously the key point is you need to have the right people in the room who understand those different educational environments in order to do that kind of building. We also have a very robust collaborative network, including many of the industry field leaders and employers, as well as representatives of other major national initiatives in quantum, DOE NQI centers, National Quantum Initiative Centers, like QNext at Argonne, NSF, Quantum Leap Challenge Institutes, other national networks. And in the blue call-out boxes here, you can see some of the points of collaboration that we've identified. So this slide is really the meat of what we're trying to do. And this is both a new way of developing content and hopefully giving rise to new content itself. And so on the left, we have inputs, on the right, we have outputs, and you can see just the breadth of inputs here is itself not traditional. Normally when one's developing a new class, it's sort of one faculty member at a university looking through various textbooks and review articles, trying to synthesize the information. And there's some of that happening with our subject matter expertise, but we also have representatives, industry and national labs helping to develop the curriculum. We're also very tightly partnered. Roughly a third of our team is not necessarily physicists and engineers specializing in quantum information, but in fact, researchers who specialize in education research, and either broadly STEM-based education research or specific discipline-focused education research, like physics education, chemistry education, engineering education. And so what they're able to do is both inform our curriculum development based on what we already know about how humans learn, which is not in the basic training of a physics PhD. So this is important information in learning how to design a class. But because these people are themselves academic researchers, they can also, for example, do surveys and focus groups and engage with employers and industry and really help us to align not just specific topics, but really what should our students be able to do? Like what does the output look like to ensure success, not just in an academic track, but in the variety of entrepreneurial and industrial positions that are emerging in the quantum economy. And so as part of this, obviously, it's critical to train both ourselves in this initial phase, and then also to offer as a service to the academic community once we have everything up and running. One of my colleagues, Andrew Heckler, has a great saying that there's no such thing as an instructor-proof curriculum. So doing some of this initial training is important, and then really the rubber meets the road. I mean, when you try and teach a class. And so one of the challenges of this cycle is you can't learn anything about a semester-long class at a pace faster than one semester. So, we need to develop the curriculum, but also teach it. And then these education researchers are doing assessments and studies of what we're teaching and what works and what doesn't, which feeds back into the cycle. So our outputs are quantum aware students and quantum aware faculty. I guess you could expand that faculty piece a little bit to say we're taking subject matter experts and teaching them how to teach effectively, and taking science educators who maybe don't have the specific quantum information background, because that's still a relatively small cohort of the community, and training them in the fundamentals of quantum information so that both groups can deliver this pedagogy. So this stuff is a little bit legacy for NSF. And I don't want to spend all my time talking about this, so I'll just quickly say this is sort of our prototype target for initial course development is a minor in quantum information with 4 common core classes that everybody taking the minor would take, and then 2 elective classes. And so just as a quick example, the reason we're focused on a minor and not a major is because of some of this industry-focused needs finding and appreciating that companies like Google and Toptica and Cold Quanta and IonQ don't want someone with a quantum engineering major because it's not really clear what that means. They want an optical engineer who is quantum aware or a microwave engineer who is quantum aware. And so that's sort of the spirit of what we're trying to produce here. This is not so critical. And then I think finally, maybe the last thing I'll say, and then this might be a good point to pause for questions, because I'm going to switch gears into much more of a research focus, is that we're still in the early stages of preparing this. We're teaching the first iteration of our introductory class, which is targeted at first semester freshman year right now. But so in the combination of prototyping that class and standing it up, the needs finding that I mentioned earlier, where we're going out and talking to the community of employers and scientists and engineers, and then also just referencing the research-based STEM education literature. These are sort of the 4 key bullets. So the first 2 are conceptual, the last 2 are a little bit more operational, but a key point here is that if we want to make the curriculum more accessible and more compelling to a broad range of students, it's important to find a way to front load applications and conversely backload the formalism. So this is a really important point that I think is backwards from the way we currently teach most STEM classes. So certainly speaking, for OSU's physics major, we start off really with a large math front loading, and it's not often that well motivated. It's, take this calculus class because eventually you'll be able to use it for science, trust us. Then after that, take this other calculus class and another one, then some differential equations, right? And it's not till really the junior and senior year that you start to really engage with compelling problems more than, spherical collections of charge or blocks on planes or something like that. So it's not that the formalism is unimportant. Clearly it is. We want to produce students who are well-grounded and able to tackle challenging problems, but it maybe doesn't need to be taught first, especially in 2022. And I like to sort of use a graphing calculator analogy here that, with a graphing calculator, you can learn a lot about how functions behave without having to understand all the mechanics of how to derive and manipulate those functions, but you can get a qualitative understanding that then motivates a deeper dive into the formalism. And I think that benefits all students. I will say, as a consumer of undergraduate trained scientists, one of the first things I have to address with many first-year graduate students is the fact that all of their training has been heavily formal, and they really don't have the broader problem-solving context or a picture of how all the different pieces of science and engineering that they've learned fit together. And so this idea of front-loading applications and fundamental concepts, I think, is important for all students. And then on the more logistics front, what that means is instead of teaching quantum mechanics in the 3rd or 4th year, which is sort of currently standard in the US curriculum, we need to figure out how to teach at least the quantum mechanics necessary to understand quantum information, which is not necessarily the full continuum theory, but could even be a 2-state version of quantum in the freshman year. And so that's really something different from a technical point of view. This has implications for prerequisites and other aspects of the curriculum. And then the final point is that since quantum information is such an intrinsically interdisciplinary field, we really need to figure out how to work in an integrated way across departments with co-instruction and even across universities, because the the density of experts in quantum information is still low on the national scale. So the chance of any one university having the faculty to teach aspects of quantum sensing, quantum computing, quantum simulation, quantum networking, all of that together is pretty rare. There's not many schools, if any, that really have that breadth. So I'm going to stop now on this because this is an exciting topic and I can talk for the whole hour, but I promise.
I'll just take one, since we're going to switch topics, I'll just ask one quick question. Others can also. So this is very exciting, and I should have actually said in my introduction that I specifically asked Zeke to talk about this because he had this nice, in fact, this was one of the first things I thought he'll talk about, and I'm happy to see this. One quick, so do you also now extend this to K12 Outreach also? Is that part of the program here?
It's not formally part of the program. It's an important piece of what we're trying to do. I think, from an operational point of view, we're collaborating for that. So there are K12 initiatives that are already up and running in the US, and we're talking to them. As well as, like, for example, one of our commercial partners is a company called Qubit by Qubit, which is an all online sort of zero credit approach to education, focused at the high school and middle school level. So yeah, it's important, but is not formally within the scope of what we're directly working on.
In the interest of time, I'll let you go on, but I can have more questions. I'll ask later, maybe.
Sure.
Thank you.
Okay. I think maybe somebody has their mic open.
Can you please mute your mic if you're not speaking? I mean, unless you're asking.
Well, I think as the host,
would it be possible to just mute? I'll figure out. Hang on.
We're having a little. There's always
I'm doing
it. There's always somebody has forgotten.
Yeah, there we go.
I've done it.
Okay, thank you. Thank you, Emerson. Okay, go ahead.
Yep. It wouldn't be 2022 if we didn't have at least one AV issue, so I'm glad we got that out of the way. So as promised, now I'm going to pivot and do a bit of a deep dive into a specific application of quantum information, and that's the idea of using magnons, as I'll say in a bit, that can potentially carry or perform quantum operations on their own. But I think the most interesting potential application is as sort of a glue or as a transduction medium to couple quantum information between disparate qubits. So this is research happening within my research group, but of course, we have a pretty broad network of collaborators here. We're always looking for more. People see aspects of this work that they'd like to participate in, but I want to make sure to acknowledge them all up front, just in case we run short of time. And I want to take a moment to sort of unpack some of the opportunities that exist. So here's a very nice group out of Tanaka's group, nice work out of Tanaka's group. And that's not Tanaka, sorry, I'm blanking on the name right now, but the reference is accurate, so people don't have to rely on my shoddy memory. But the basic idea here is using a magnon, which is a dynamic excitation of a ferromagnet, in the same way that a phonon is a dynamic excitation of an atomic lattice. So you have these spin waves or magnons in a magnetic material, and here this is a polished sphere of a material known as yttrium iron garnet, or YIG, which is sort of the gold standard for this type of work. And here, this is placed in a 3D microwave cavity along with a superconducting qubit. And this sine wave here is indicating that there's some coupling G between the qubit and the magnon mediated by the microwave cavity. And they've demonstrated, there's a beautiful series of papers here where they've demonstrated the ability at the single quantum level to measure individual correlate individual magnons with individual excitations of their qubit. For people who may be more familiar with work in optomechanics, for example, I think that there's a strong analogy here where the magnons are essentially another simple harmonic oscillator, as are the photons, and you can couple them together. It's another degree of freedom to allow you to engineer quantum states. One of the other, I think, really powerful approaches for looking at magnons in the quantum regime is in spin-magnon coupling. So this area is still a little bit less developed. So this paper here from Amir Yacobi's group isn't truly in the quantum regime. It's more in the continuum limit of the magnons, but using an individual NV center to sense the magnons and couple to them. And the potential power of this approach is doing more work on the magnon side to get into the single quantum regime. The coupling mechanism is through the demagnetizing field or the dipole field generated by the magnons. And so what I think is particularly appealing about that is that coupling mechanism is generic in the best sense of the word. So once you create an oscillating magnetic field in space, it doesn't really matter where that oscillating field comes from. If you have anything with a magnetic moment, so anything with a spin, then you will have some non-zero coupling. And so I think this is another exciting direction to look at in terms of magnons, is not just as another harmonic oscillator with quantized states, but specifically taking advantage of the magnetic and aspects of magnons to do quantum information. So all that being said, I've given sort of a high level model for these interactions, and it sounds based on my description, one might expect this field to be further along than it is. The reason why it's not is that magnonics is strongly materials limited. So experts in the talk will probably already be aware of this, but just to highlight, every magnetically ordered system has dynamic excitations, right? Nothing is ever truly frozen. So magnons exist in pretty much every magnetic material, but the question is how high quality is that magnetic resonance? So the quality factor, or Q factor, is a nice way to compare across systems. And so in order to do interesting quantum information things, we need magnons that have coherence times that are reasonably long. And to give a feel for that, the quality factor is basically the number of oscillations that a system undergoes before it decoheres. So as a point of reference, like a quartz crystal in an old school quartz watch has a Q factor of about 1,000. A high quality optical resonator has a Q factor of about 10 to the 6th. Most magnetic materials have a Q factor of about 10 to 100. So while the theory can go far with this approach, in terms of practical implementations, it's a substantially bigger challenge. There's really only one material so far that has sufficient coherence that one can start to play these games for quantum magnonics, and it's this material YIG, which is in a thin film form in the upper left, or macroscopic polished spheres in the bottom right. Again, just for experts will already be aware of this, but anyone who's ever worked with a network analyzer, there's a sort of a frequency tunable component that works in the gigahertz frequency range. That's as indicated here, is like a millimeter polished sphere of bulk YIG on a bar, and you essentially move it back and forth through an inductive coil to tune various microwave filters and coupling. So the state of the art in microwave electronics and in high frequency magnons is not as advanced as one might think. So to to then look for paths forward, this is just a quick high-level slide making the case for chemistry as a place to look, and in particular for molecules and molecular-based materials. And so what the images here are meant to represent is sort of, I think, in most physics departments, we're used to, in the solid state context, used to working with the periodic table. And so if you look at that, that's a lot of variety. There's a lot of different compounds that one can form there. But ultimately, you're limited by the atoms that you've got, the atoms that nature's given us. And there's a lot of flexibility within this table, but not an infinite amount. In contrast, if you want to fine tune electronic states, which, the orbital states of an atom, chemists have figured out how to do this a long time ago. You take an s orbital and you say bond it to two p orbitals in a ligand, and this sort of gray or blue oval indicates you can sort of distort that wave function in forming that bond. And by building up more complicated ligands, you can very precisely tune the perturbation of your fundamental orbital. So this has been around for a long time. So we have a pretty huge library of very precise and fine-grained perturbations. Another advantage of the chemical approach is you can make large numbers of identical copies. But the piece that's missing is, just historically, people have not as intensively studied coherence and entanglement in these systems because it just hasn't been relevant until recently. So it's based on that intuition that I want to introduce sort of the compound that I'm going to be talking about most today is this vanadium tetracyanoethylene, or I'll call it VTCNE. So as you can see in this cartoon, it's a bulk system. So the red vanadium atoms are complexed with this TCNE small molecule. The TCNE is basically an H made out of carbon with a double bond at the crossbar and nitrogens at the terminus. So the chemically active piece is a vanadium nitrogen bond here. And the vanadium gives up 2 electrons going to the 2+ state. That then reduces 2 TCNE to the TCNE minus, and we get ferromagnetic order with a large spin on the vanadium site anti-parallel to a small spin on the TCNE site. And so I just want to quickly say this is not a small molecule. This is not a single molecule magnet. It's not a polymer. It's actually a 3D structure that the chemists tell me I should refer to as a coordination compound. So if you want, you can think of any binary material like gallium arsenide, but instead of at one of the lattice sites, say keep the metal atom, keep the gallium, but instead of an arsenic, you substitute in a small molecule. And that's basically how VTCNE is structured. So looking at this, though, this sort of violates all the basic rules of where one should look for a good magnet. The spins are relatively far away. The material is largely disordered. There's not long-range structural order. It's more polycrystalline at the borderline of being amorphous. So none of those things should give you confidence in the magnetic properties. And you might expect me to start talking about, millikelvin temperatures or something to that effect. But in fact, quite surprisingly, this is an extremely robust ferromagnet. So the ordering temperature or Néel temperature for the material that we're producing currently is about 600 Kelvin. So this is material grown by chemical vapor deposition, which evolved from an initial solution phase synthesis. You can see M versus T here is relatively flat, but it has quite nice hysteresis and sharp switching and saturation at low field. In addition, because it's a molecular-based system, the CVD is actually quite modest environmental conditions. So the pressure at where we grow is a few torr rather than 10 to the minus 10 torr for a UHV system. And the temperatures are about 60 degrees Celsius. So this is actually magnetic spray paint effectively. You can put it on top of pre-patterned device structures a wide variety of substrates because it doesn't care about lattice matching. And across all that phase space, you maintain this robust magnetism. So that alone is sort of a very interesting scientific puzzle. But the thing that really got us worked up over the past few years working with this system is when we look at the magnetic resonance properties. So here on the inset is a single FMR resonance line scan where the frequency is just a few megahertz. If you track that line width as a function when varying the magnetic field and hence the magnetic resonance frequency, this slope allows you to disentangle the inhomogeneous broadening, which is this intercept, from the homogeneous broadening, which is this Gilbert damping parameter alpha. And I mentioned before that YIG has been the gold standard for 50 to 75 years for microwave electronics. And this, again, I've sort of generalized to the Q factor that one can find in YIG. You can see this is a really good quartz crystal or a pretty bad optical cavity is the phase space that's available. The Q factor of VTC&E beats YIG thin films and is comparable to YIG spheres. And this number is improving sort of all the time. The more precise figure of merit that people in the magnetic resonance community will appreciate is this alpha, and this value of 4 times 10 to the 5th. So this Q factor is essentially the total line width, homogeneous and inhomogeneous. For many applications in quantum information, it's really only the homogeneous broadening that you care about, and this is superb. Right. So this is pretty routine. This is not one hero sample that generated this value. So this really is foundational, and we believe ultimately will be transformational for the field. And here I'm referencing a theory paper that we recently put out in collaboration with the Flate group. We put out, really the Flate group put out, and we contributed to along with the Fuchs group at Cornell. And what we're looking at here in this diagram, the schematic, the green is a disk of VTC&E. And so this is essentially a Magnum resonator deposited on the surface of diamond. And then what they've done is assume some distribution of NV centers in the diamond, and then take line cuts as a function of depth or across at a fixed depth across the disk. Sorry, my pointer was backwards when I was saying that. And calculated a parameter known as the cooperativity. So there's without worrying about the precise mathematical form, the essence of what the cooperativity is telling us is that if you want to do quantum information operations with a given qubit, then you're essentially comparing 2 different timescales. One is the timescale at which that system decoheres or loses or dissipates the quantum information. And the second is the coupling rate, how quickly you can talk to that system. So for a cooperativity of 1, that's sort of the minimum threshold for being able to read out or write quantum information to a system. And what we're looking at here, which I probably should have said at the beginning, but is at the top of the slide here, is the spin-magnon coupling. So we're looking at how, if I have an NV center somewhere in the bulk of this diamond, and I flip it to change its quantum state, that can then excite a magnon in the VTC&E disk. And so the cooperativity measures how the fidelity with which we can do that. And this dotted line is at a cooperativity of 1, which as a function of depth, you can see down to 125 nanometers, which is quite deep into the diamond. So you're well isolated from the effective surface spins. You surpass this cooperativity threshold. This X cut is just moving across the disk. So if the edge of the disk is, say, here for 240 nanometers beyond that edge, you'll still have a pretty high cooperativity. So what this means is that the magnons in VTC&E are sufficiently coherent that if we can build a structure like this, we should be able to use it to read and write quantum information to an NV center. But even more compelling is since magnons are delocalized excitations of the entire system, right? This is a magnon cavity. You can think of it as in terms of cavity QED. It does many of the same things. If I have one NV center over here, another NV center on the other edge of the disk, I can actually couple those two NV centers to make either a bus for quantum information, if you want to think of it that way, or to create a hybrid qubit, if you want to think in that context. And coming back to what I said earlier in terms of spin-magnon coupling, my second qubit doesn't even have to be another NV center. It could be any other point defect, any other spin qubit, molecular system, atomic system, whatever you're interested in. So this is the target. And then the question is, well, okay, so historically, we know thin films of VTC&E have appropriate parameters. What happens when we actually try and build these resonators, at micron length scales, and can we pattern, et cetera? Of course, that's a bit of a straw man. I wouldn't ask that question in a talk unless the answer was yes. And so I'll just quickly say we use a modified e-beam lithography technique to essentially do an in situ shadow mask. We do CVD through a window in the PMMA-MMA bilayer. And you can see in cross section, we get this sort of lens-like structure. This has to do with the fact that this is a CVD process. So people used to doing device fab are used to the low pressure regime where sort of atoms come down directionally. Here we really have some gas flow dynamics that are giving rise to this shape. But the important point, and actually I realized I don't have this data on the slide. So on the left-hand side, you can see we can make just about any pattern we want, just limited by the fidelity of e-beam, which is quite good. But if we look at the damping in these disks, we get exactly the same value of 4 × 10⁻⁵ that we do for thin films. So this is itself pretty unprecedented for magnetic systems. Patterning magnetic systems almost always leaves edge states that contribute to damping or dephasing in the dynamics. And using this patterning and growth technique for VTC&E, we completely sidestep that. The other thing I want to point out, and I know there's a lot of data here, this is characterizing both bars and disks, but this bottom right corner here, the blue is experiment and the next two panels are theory. You can see here, we see harmonics of the fundamental mode up to 7 that we can identify both analytically and numerically. So this green is a numerical simulation where the arrows are representing the harmonics that we see in experiment. You see a lot more peaks in the simulation because not all magnons have the appropriate symmetry to couple to the cavity that we're using to do the measurement. So that's not actually a failure of the theory, the fact that we see more peaks here. And importantly, this numerical modeling allows us to develop here, these are basically spatial maps of the magnon mode in a cross section of one of these disks. And you can see again, the taper of the sidewall here up to the 7th harmonic, we get very good quantitative agreement with the experimental behavior. So what this means is that we can make specifically the simple structure that we used for that initial theory proof of principle, but we can really make an arbitrary shape for our magnon resonators, magnon waveguides, and precisely predict and engineer what those magnon modes will look like. So in the interest, so there's a lot more to say here, which I'll maybe skim through a bit, just in the interest of time. I will say that another interesting recent result is that using a focused laser spot, we can locally damage the VTC&E, which effectively erases the magnetism in that region. So here in this published work, this is just an initial proof of principle that we can pattern the VTC&E. We have a paper in progress in preparation where we show that we can use this to make patterns very similar to these e-beam lithography patterns that show the same behavior, that show that we can make Magnum resonators, and there's a toy in the US, the Etch-a-Sketch, which you may or may not be familiar with. You basically just draw the pattern you want with a laser spot as an alternate patterning mechanism for these systems. You can also, because it's CVD and conformal growth, you can get 3D structures, which we can also model very precisely and in good quantitative agreement with theory. So we're getting close to the end of time. So maybe what I'll do is, so this is just, I'll just talk a little bit about some final application notes for potential uses in quantum, and then maybe stop and open the floor for questions. So as a technical detail, again, people who in the audience who have studied magnetism, these 3D structures look kind of like nanowires. And in fact, we see an in-plane magnetic anisotropy. So that's initially intuitive, but then we realize the length scale of the density of the packing here is such that from a magnetics point of view, this should act like a thin film. There's not going to be significant in-plane demagnetizing field, yet we still see an in-plane anisotropy. And in fact, the easy axis for that is oriented perpendicular to the long axis of the wire, perpendicular to the direction that one would expect to see. And so this was a first hint at an additional sort of degree of freedom here, which is to say strain. So our hypothesis was that the curvature of the substrate is introducing some strain into the system. So we wanted to test that out. The easiest way to do that is just bond a VTC-NE film to a piezoelectric. We chose PMNPT and see what happens. So these initial panels are just characterizing that, yes, this is reasonably well-behaved VTC-NE. The line width is somewhat broader than the optimized films I showed a moment ago, just because of engineering them into this piezo geometry. But the important point is, as we apply bias to the piezo, you can see a significant shift in the ferromagnetic resonance frequency of the VTC-NE. And that, in fact, we can get a shift at maximum strain of 4 to 5 line widths. So to put that in context, here there's a more systematic study where we show that this tuning is reproducible over 45 megahertz, and the damping or the loss by any measure, whether it's total line width, inhomogeneous broadening, or homogeneous broadening, we see no change over this strain. So this is a very reproducible and benign perturbation of the system, but it allows us to tune in situ the magnetic resonance. And I really want to point out that this is yet another remarkable feature of this material system, that there's a 2 order of magnitude larger tuning, a larger magnetoelastic coefficient lambda sub s than YIG. So that's huge. So basically you can't really detune YIG with strain, is what that means, where we can with VTC-NE. So again, people who may be familiar with the field may say, well, but there are much larger, YIG is not really a good magnetoelastic. There's a number of famous compounds, for example, galphanol, that has much larger tuning, which is true, but it also has much larger ferromagnetic resonance line width. And so in fact, this metric that we're sort of inventing here of 4 to 5 line widths of tuning with strain is at the leading edge of the maximum strain tuning that can be seen in any system. So this is pretty powerful, and as I'll show in a second, we believe that dynamic range is in fact limited by the piezo, not the material. And so this is a little bit out of chronological order. But I'll circle back to talk about one last piece, So I've shown that we can make these disks. They're high quality. I've maybe even shown some ability for in situ tuning. The last implicit requirement for applicability in quantum information is the temperature dependence. And so we need these things to be able to operate at cryogenic temperatures in order to freeze out the thermal excitations necessary to do real quantum information. And so this data actually came in advance of the intentional strain tuning, which is looking at, again, the magnetic resonance line width effective, or equivalently, the effective anisotropy field as a function of temperature. And so you can see that this tunes through zero to a negative value. And the magnitude of this tuning is enormous. So this is no longer, I apologize, in magnetic resonance, we bounce back and forth between frequency and field representations. So a typical line width in terms of field is 2 to 3 Gauss. So you can see this line width tuning is over 100 Gauss. So 40 or 50 line widths of tuning as the difference in thermal expansion coefficient between the thin film and the substrate drive a very large strain in the system. And this tuning through zero does two things for us. First, it actually provides additional insight into the structure, and that it suggests there's a crystal field anisotropy that's been hiding for the last 15 years in this system because it happens to be pointed anti-parallel to the shape anisotropy. So all of the systematics that one would do to look for an anisotropy field can't distinguish between those two contributions. That's why we label this H effective rather than M effective or M sub S. So that's interesting from a fundamental science point of view. From an applications point of view, this points out that using this strain tuning, we can not just modulate the magnetic resonance frequency, we can tune into a zero anisotropy regime, which is very interesting for looking at sort of more exotic magnetic resonance tricks that we might want to play. And this is the last slide, and then I'll open it up for question. The other key parameter, of course, though, as a function of temperature is the line width. And you can see that the line width actually gets worse as the temperature goes down, which might be initially counterintuitive, but then comes back down to recover the room temperature value below about 10 Kelvin, as you can see in this inset. So this orange curve isn't just a guide to the eye. This is actually a theoretical calculation. And again, for people who may have been following the magnonics literature, of a significant challenge to working with YIG in quantum applications is that YIG exhibits the same behavior, only about 6 times larger amplitude in terms of the line width broadening. And so this orange curve is a theory developed for those YIG studies, where what people eventually appreciated is that what we're seeing here is scattering between the magnons and paramagnetic impurities in the system. And so I'll give a quick hand-waving explanation for the full version. I encourage you to look at the paper here. Our theory collaborators have worked this out in detail. But sort of in broad strokes, you can think of this high temperature regime where the line width is increasing as arising from the fact that at room temperature, our paramagnetic spins are perfectly unpolarized. We have just as many spin up as spin down, but only one of those two spin orientations can scatter magnons, because all our magnons essentially have the same angular momentum, either +1 or -1, depending on the direction of the magnetization. So only half of those spins can contribute to spin magnon scattering, because the other half, the angular momentum, would not be conserved. But as you cool it down and those paramagnetic spins polarize, more and more of those spins are in the state that can scatter magnons. So this downturn at low temperatures is when some new physics takes over, however. And here we have to move beyond that quasi-equilibrium view and really look at the dynamics, which is, I think, kind of fun. So if you start thinking about the spin lifetime of those paramagnetic spins, which should be continuously increasing as the temperature drops, and the Magnon scattering time, that mean Magnon scattering time. So how long after the first Magnon hits it does the second Magnon hit the same paramagnetic spin? And what happens is at very low temperatures, the coherence time of those spins gets to be long enough that they're essentially synchronized and phase locked to the Magnon excitations, at which point they can, again, no longer efficiently scatter Magnons. So this is why you see this dramatic drop in the damping at low temperature. So this is to 5 Kelvin because this is what's easy to do with bulk samples. We're working with our collaborators at Cornell to get these measurements into the millikelvin range. And I just want to emphasize that the fact that this is comparable to the room temperature values means from the very early slides in my talk, this is better than the best thin film YIG and getting close to polished YIG spheres. And assuming no new physics crops up, and we don't anticipate any, but you never know, as we continue to millikelvin temperatures, we believe that there's a good chance that we'll see the lowest damping ever measured in a magnetic system. We expect to see another factor of 5 to 10 decrease in the damping and may even be approaching lifetime limited line widths for the Magnon excitations, which would be really sort of a cavity QED type regime for those Magnons. So as promised, I will stop talking here and open the floor up for questions.
Thank you, Zeke, for that wonderful talk. And it's very glad to see the VTC work sort of progress over the year. Now it's looking really, some very nice fundamental physics that you can get to. I have a few questions, but I'll open the floor and let others also have a chance to ask questions. Please go ahead. If you have either type in the chat box or you can unmute and ask also.
Hi, Praveen, can I begin?
Sure. Hi, sure. Yes.
Hi. So hi. First of all, thank you, Zeke, for this very nice overview. It's not only is the research fascinating, but also to see how you're unfolding a very multidisciplinary quantum program. It also serves as a motivator for us here. But back to the science, I'm just wondering what motivates the choice of this particular molecule, or like how did you find this sweet spot?
Yeah, I really wish I could say it was my deep scientific insights and my brilliant thoughts. But as with many things, it's sort of a combination of good fortune and being prepared to capitalize on that good fortune. So the two people who pioneered this VTC&E material are Art Epstein and Joel Miller. So Joel Miller is a chemist at the University of Utah. Art Epstein had a joint appointment in physics and chemistry at Ohio State before he retired. And so when I started as an assistant professor working, focused more on spintronics at the time, this was around 2006. Art, was in the same department. He was working with this molecular-based magnet, and so we just sort of started working together. And in a more traditional spintronics context. So I think the first paper we published was using the VTC&E as a magnetic electrode for a 3-5 LED structure to do what's known as a spin LED, which is one way to measure the spin polarization of a charge current. And so we got that working, which was surprising, and I believe a first at the time of being able to extract a spin polarized current from a molecular based system. But then, that direction for spintronics was not necessarily slated to, on the track to continue, because, you're not going to outcompete other existing materials. So that is to say, it worked for physics standards, but not engineering standards. But then sort of almost as a side thought, just because Ohio State also has a strong history of FMR, and in particular, Chris Hamill-Vidya's PhD advisor is one of certainly the world experts in that area. So we had access to this facility, and we're like, well, we don't really understand the magnetism in the system. Let's just try some FMR to see what it looks like. And maybe that'll give us some insight. And that data actually initially sat on the shelf for about 6 months because it didn't tell us anything about the magnetism. The line widths were really narrow and didn't change under any perturbations. And we were new to that aspect of measurement. We're like, okay, well, that's boring. And then, several months later, 4 to 6 months later, one of my student working on that program sort of was reviewing it and comparing it to literature and sort of brought to me a benchmark of trying to understand what the FMR meant. And he just listed, the line width of permalloy, the line width of cobalt, and the line width of YIG, and just sort of know, oh, well, this is about YIG. And, I don't think he thought much deeper than just finding another material. But so that was sort of the light bulb going off. It's like, oh, wow, that's actually really hard. People have been looking for over 50 years for anything other than YIG that exhibits this low damping, ultra low damping. So that was some time ago, and as Vidya noted, this work has been progressing for a long time. The challenge. So it's exciting to work with a new material, but definitely one of the challenges is it takes a while to build up an understanding of all the structural electronic aspects. And maybe I'll use that as an excuse to skip ahead and just say a paper that we're getting ready to submit now is a joint DFT EELS measurement in TEM, where the DFT has predicted the energy structure of VTC&E with quantitative agreement to experiment for the first time. And it gives us this sort of cartoon picture of a spin resolved density of states where the equatorial TC&E, from the frame of reference of the vanadium, are these blue orbitals, and the apical, the ones pointing out of plane for the octahedral coordination, are these green orbitals. And this splitting is huge for energy length for relevant energy scales. It's about an EV, and so this yields all kinds of interesting physics. So it's a fully spin polarized band gap. For one, it gives us some hint of where this strain dependent anisotropy comes from, because there's an inherent magnetic anisotropy in the crystal structure and various other things that are off to the races here. So we're very excited about this. This is hot off the presses. And I think this is not yet an answer about why this particular material. So your question was how we found it. And the answer is basically by being lucky. Then the next question is, well, what does this tell you about what other materials may exhibit this behavior? And for a while, we've been kind of throwing darts, trying to make educated guesses about what other systems might do this. We don't have the answers yet, but this now gives us the foundation, I think, to start asking those questions in a much more quantitative and concrete way. So I'm pretty excited for the next couple of years. I think we have an understanding of this class of materials where we can start looking for other systems.
Yeah, indeed, fascinating. Thank you for the, very brutally honest answer, I would say. I'm just reminded of a quote that my friend often likes to say. She recalls Louis Pasteur, who said, I think fortune prepares the prepared mind or something like that. So yeah. I guess there's a lot of effort going behind your, what you call serendipity, but probably it's insight in another form. I'll leave the floor for others to ask questions.
It's very generous of you. Thank you.
Thanks, Zeke. Yeah, this DFT works really looks interesting and in this band structure, but I'll go to a chat box. I have a question from Professor Mahindaran from NUS Singapore. And he's saying that for a while, TC seems to be nearly 300 Kelvin for a long time, but seems to have increased to excess of 600 K over the last few years. What makes it so? That's the first question he's asking. So.
Sure. Yeah. So I think there's two stages to that. The first was switching from solution synthesis to CVD synthesis. Sort of took us from 300 to 400. And I think the key element there is that in the initial, in the literature, solution synthesis, there would solvent atoms would be trapped in the lattice, and that would lead to even more disorder than we have in the thin films. So going to CVD is a solvent-free process. It's a gas phase reaction, so that just wasn't a problem. So that was one benefit. And then I think the secondary benefit was basically just the second aspect was just learning how to do the CVD well. So a moment ago, I commented about, the challenges of working with a new material, and this is one of them, is that, figuring out really what is the optimal phase space for growth of a new system is a many year endeavor, and is frankly still ongoing. We have an upgrade to our reactor that's just about to go online that we hope will give us even more precise control of the deposition and the material parameters. But that second step at some level was not any unique deep insight. It was just sweat equity of the relevant graduate students and very carefully sort of optimizing the growth. And I guess I'll say the one thing maybe to bring to the problem, and I think this is a strong argument for interdisciplinary work, is that prior to my group getting involved, all of the synthesis had been done essentially from a chemistry perspective. And my materials background personally comes from the MBE world, right, which is a very different way of looking at materials. And they both have their strengths. I think chemists are great at discovering qualitatively new compounds and materials and phenomenology, as I think that VTCNE is a perfect example of that. From the physics, solid state materials perspective, more of an MBE perspective, that's a field that has really, perfected precise control down to a part in 10 to the 6th to a part to 10 to the 8th, just really, really precise control for semiconductor MBE, because any small level of impurity gives you doping and affects device performance. So in addition to just sweat equity, it was one of the things that we contributed to the field, I think, was taking that more precision-oriented mindset to the synthesis challenge and really regularizing the reactor design, the systematic way we went about mapping out the growth phase space. That is, I think, just more time and detail than typically happens in synthetic chemistry, because they demonstrate the compound, get an initial read of its materials properties, and then move on to trying to synthesize another compound, which is great, which is also a very useful contribution to science. But at the interface between the two fields, we would not have had anything to optimize if the chemists hadn't discovered this material. But maybe somewhat immodestly, if there hadn't been a more solid state materials perspective brought to the system, it may not really have optimized up to the level with the very narrow single peaked resonance for the FMR that we're seeing now.
Just a couple of more questions from him. One is long-range ferromagnetism established in this compound by neutron diffraction? And the other question is, I was under the impression that resonance field decreases with lowering temperature in ferromagnet, but this shows opposite behavior. So last second slide, comparison at 300K and 5K. Can you explain?
So first, the short answer is no on neutron diffraction. And that is partially because, well, I would say in large part, just because the samples are air sensitive, which is not a showstopper, but makes those measurements more challenging. More importantly, they're thin. And neutron scattering typically needs a pretty thick sample. So we've made a couple of attempts at stacking multiple samples together and trying to get them shipped to a neutron beamline, and it's a very challenging experiment, is I guess what I would say. And there's only really 2 groups in the world that are actively producing this material at this point. Joel Miller's group is still working on it, at least they were. As of a few years ago. Our group, well, I should qualify that we're part of a DOE EFRC, which is evenly split between physicists and chemists. And so some of the chemists in that center, like Jeff Long's group at Berkeley, material scientist Mark Hersom at Northwestern, are now revisiting VTCNE from that perspective. But there's it's just a bandwidth issue. So the combination of those two things. So the second question about the magnetic resonance field. So temperature dependence depends strongly on the material. You might see a slight increase in M sub S as temperature decreases if you're looking at a metal. Right, the M versus T is pretty flat, and that saturation magnetization is ultimately what's going to control the magnetic resonance frequency. But you have other systems with steeper M versus T curves where you would see a bigger effect. Here, what we're dominated by is not any intrinsic temperature effect, I would say. This is not formally the temperature affecting the magnetic resonance. It's the temperature affecting the strain, and then the strain affecting the magnetic resonance. So I think by far the dominant effect of this variation of over 100 Gauss, which is basically 100% or 125% tuning of M sub S, right? So we go from a positive to a negative value. If we had an easy way to get this calibration, we should perhaps have a second axis that is just measuring strain as a function of effective field. And that's really the physics that's driving this.
MSR, I see. Please go ahead.
Yeah. So Zeke, very interesting talk and pretty exciting material, VTCNE. So I have a couple of questions. Sure. So what is the typical spatial separation between the VTCNE magnons and the spin coherent NV centers? In order to see the coupling, what should be the...
So here's as a function of depth.
Okay.
And so, we picked 30 nanometers as sort of our design parameter because from the NV community, this is the depth at which you stop being particularly sensitive to surface spins. Okay. But in principle, up to over 100 nanometers. So I will say, to be fair, this is a theory paper, predicting optimal performance. So this is assuming that one has optimal NV coherence times, right? Which for people working in the field, I don't have to say that's not very easy to do at all. There's only a handful of groups that have demonstrated the ability to get coherence times that long. But that being said, qualitatively, this cooperativity parameter, if you're outside the field, it's hard to know, like, okay, so 1 is a threshold, but should I think of it in a log scale or how big is big? So I don't have the exact number, but like the cooperativity for talking between 2 superconducting qubits is not much different from 10. These are very high cooperativities from a quantum information perspective. So there is some room to compromise on any of the specific parameters used for the calculation. So, would you get exactly these values? Well, it's hard to do an experiment as good as the theorists propose for us, but I think we've got some wiggle room.
But 30 nanometers is a good challenge for experimentalists, right?
Yeah.
Okay, that's good. So my other question is, so the Magnum detection that you see in VTCN, is it thickness dependent? You see any dependence of the thickness of the FMR signal?
Yes. Come back to this data. Okay. So this is the FMR signal from an array of disks. And I mentioned that these are essentially harmonics of the fundamental mode, excited, higher level quantized states. So for these disks, it's a 3D quantization, right? So you have a lateral confinement from the perimeter of the disk and a thickness confinement. And so in this size scale, The thickness confinement is the dominating quantization parameter. So the radial confinement shifts the position of these peaks a little bit, but that's more the perturbation on top of the thickness. So as the thickness changes, you would see the spacing of these peaks move. And so this is, I apologize, it's smaller, it's a little harder to see here, but the fact that we get quantitative agreement, these black vertical bars are an analytical calculation of just sort of taking a disk of VTC, a perfect disk of VTC and doing some plane wave modeling to predict where you expect those harmonics to lie. And then the green data is a full numerical modeling using MuMax as sort of the tool of choice for doing this sort of magnetization dynamics. And they all agree. All three agree. So the first and the biggest impact in this context would be changing the quantization conditions. In terms of whether there's a thin film versus a thick film regime for the quality factor or the nature of the magnetic material, we don't really see any evidence of that, at least not yet. So it could be that there's some modest effect that's being swapped by sample to sample, just growth variations. But we don't see anything systematic in looking at the damping. And we have some cross-sectional TEM that does not show any variation through the thickness of the film beyond maybe very thin interface layer.
Probably one could also do inverse spin Hall effect to see the effective thickness, I suppose.
Yes, so that's a whole different direction of research that I didn't even have the chance to talk about. So this material really is amazing. And it turns out, so the Utah group has done ferromagnetic spin pumping into platinum and measured an inverse spin Hall effect that is very measurable. I mean, those measurements are harder to calibrate in terms of an absolute sense. We have, again, another manuscript in preparation with the Harriman's group at OSU looking at spin thermal physics. And so there one can calculate a spin-Seebeck resistance, which is just to say a fixed heat flow, what's the transverse voltage that I get in a platinum bar. So that's easier to compare across material systems and compare. And again, VTC&E gives the same value as YIG. So that I was completely astonished by. In fact, that's another project where the student working on it, Seth Kerfman, was bugging me to try that. And I basically told him not to waste his time. I was like, so the magnons and VTC&E are different than YIG, and it's a molecular-based system depositing that on a metal. Who knows what that interface looks like? And you're effectively doing an exchange interaction at the platinum magnet interface, and who knows what exchange looks like between such dissimilar systems. So you're never going to see a signal. And he did it anyway, as a good student will do. He just sort of stopped bugging me about it and found a Harriman student to do a pilot study. And it turns out the spin-Seebeck resistance is at least as big as YIG platinum. May even be larger. We have individual samples have shown substantially larger values, but we haven't been able to reproduce that, so we're not quite sure where that might be coming from. But definitely the spin-Seebeck resistance is at least as big as YIG, and there is a thickness dependence there as well, just due to the Magnum diffusion length in the VTC&E. But again, that diffusion length is quite long, so we can only really place a lower bound on it. So it should not be a linear function. It should saturate, but we only can measure in the linear regime because once we get up to it's hard for us to grow films thicker than a few microns, and we would really need like 100 micron films to be able to do that measurement correctly, or over the full range. Let me say it that way.
Very interesting. So, what about the stability of this VT CNA? It's quite stable once you form it in the thin film form. After
it's moderately stable. So I think I mentioned briefly that it's air sensitive. So one needs to be careful. We have some epoxy that we can use to encapsulate.
Okay.
You can also just build measurement boxes that can go into the glove box and then mount your sample and then seal it and take it out. Assuming one does those protective measures, the lifetime is about a month, say, on your desk. Or we haven't done a systematic study just because it's hard to measure on time scales, longer than that. But 2 to 3, if it's in a glove box in a freezer, 2 to 3 months is not unreasonable.
Great, thank you. Pretty exciting. Yeah. I think there's a question in the chat box, Praveen, from.
Yeah, there's one question from Sriram TN, and he's asking question. Bias-induced strain seems to give better alpha values. Is that an advantage?
So it absolutely would be, but unfortunately, they give worse values. I mean, it's confusing in terms of, do I want my alpha to be big or small? But the alpha is larger by about a factor of 2 in the films that we use for the strain studies. And so and in fact, that's just a measure of that particular growth and the type of substrate we needed to use to mount it to the piezoelectric. It's because it's flat as a function of strain. So in fact, and this is quite surprising. At a guess, it maybe has the same origin as to why we have such low damping despite the lack of long-range structural order at the atomic scale. But straining it doesn't seem to introduce additional damping. And it's not at all clear why that's true.
Okay. Are there any more questions from other people? Okay. I don't see, then I'll probably ask a couple of questions of my own. So first is on the science part. So one is, if I'm missing, I think I should probably know the answer, but for the patterning, when you do you do this in the glove box, or how are you getting over the air sensitivity?
It took a little bit of work. There's a couple of tricks. So the first is that, so we make the pattern outside the glove box using typical sort of standard e-beam lithography. Then before we deposit VTC&E on it, we deposit a thin aluminum oxide layer, because VTC&E, it turns out, is solvent sensitive.
Okay.
And so if you don't cover the resist with something, then the solvent outgasses during growth and poisons the growth. So then once we have the aluminum oxide down, we take it into the glove box, do the deposition in the glove box, and then do liftoff in the glove box. So the liftoff is also itself a challenge because liftoff requires solvents, right? And so this is why this is an e-beam process and not a photolith process. So one of the nice things about working with magnons is their wavelengths are quite large. So you don't actually have to go to e-beam lithography to get into the quantum limit like you do for semiconducting systems or metallic systems. But it turns out that there are certain solvents that VTC&E is okay with and others that it is not. So THF and chlorobenzene are both pretty benign for VTC&E. So we did test soaks in chlorobenzene for an hour or so, and it didn't change the FMR properties. Chlorobenzene removes PMMA, MMA, but not photoresist. So any new material, there's always some kinks to work out in the fab process, but this turns out to be a very narrow lane. This is actually another project, I should say, Andrew Franson, the first author on this paper, where he really wanted to try E-beam patterning. And we were working with shadow masking and other approaches. And I was like, that's not ever going to work. The solvent poisons it, and like, how are we even going to do liftoff? And again, he correctly ignored me and said, I really want to try this. And he did it anyway, and then showed me the results and showed me that the FMR spectra are fine. Well, okay, so there we go.
Lots of good lessons for the students there. You can go against just advisor, but make sure you get it.
As long as you're right.
Otherwise, this won't be the story that will be coming out.
Exactly. Yeah.
So a couple of just one. So the NV part. So is coherent driving part of the roadmap somewhere? So I'm guessing that's in the now with the bias control that you have, or with the piezo control. I would think that you probably can approach coherent control between the two to be there much better.
Yeah, so we're definitely pursuing that. I think the challenge is, you can go to low field to reduce the FMR frequency to an extent, but it's still a pretty challenging regime for acoustic modulation. It's hundreds of megahertz to gigahertz is tough for most oscillators. So there are MEMS structures that can do that, but then we're limited by sort of mass loading of putting a thick layer of VTC&E on top. So those are not necessarily fundamental challenges, but they're significant technical challenges. We have some ideas that we think might work, but we're still sort of pushing through that.
I know it's getting quite late. I mean, people here late enough for their leave dinner.
Praveen, one question. So this piezo control, you actually grow VTC&E on PM and PT?
We tried that. I think it might work for single crystal PMNPT, for flat single crystal. But the transducers that we ended up using that worked best were polycrystalline. And so this is one of these things that, going all the way back to my postdoc, is still a lesson I need to relearn. These link scales, are not tactile link scales, so it's easy to lose track sometimes. So like the surface roughness of a smooth polycrystalline film is still, 50 nanometers. And given our few hundred nanometer film thickness, that roughness, I think, substantially degraded, gave a lot of Magnon scattering. So what we ended up doing was growing on a glass slide, and then using some of this epoxy I mentioned a moment ago for encapsulation to essentially epoxy it down to the electrode surface.
We actually grow these oxides to a good degree of surface roughness and quality using pulse laser deposition.
Mm-hmm.
They're also quite nicely oriented on substrate like strontium titanate. So you probably could try your VTC&E growth on these films.
Absolutely. And so, yeah, I think, you could tell from the cartoon image, this is not particularly sophisticated piezo actuation, right? This is just like the first order, let's just bend it and see what happens. So yeah, we'd definitely be interested in that. We're a little bit bandwidth limited in terms of the sample fab. So if you also have collaborators who are interested in maybe patterning it into interesting structures, putting the transducers down, we could put the VTC&E down, come up with some arrangement like that. I think there's definitely interesting work to do there.
Sure, great.
Thank you. Just the one last, as I said, since we are, it must be while your background is still sunrise, but I know it's well past sunrise for you and you have other meetings, I think, coming up. Just one about the teaching or the education part, which also interests me a lot. So I know you mentioned arts last time, and we were talking about a faculty in Chicago during our last meeting when we were talking and educating people using art about quantum sciences. So is this something that's still going on with a strong degree? And
Absolutely. So I think so the way our team is organized is we have various sub teams, and so the first order organization is we have sub teams per class that needs to be developed, and those teams are constructed to have diversity on as many axes as possible, which makes them a little large, which is an organizational challenge we're dealing with. But then we have a separate team that is the education research team, and they have their own education research activities that they're performing, but then they're also dropping in on the class development teams and helping them to understand sort of modern pedagogies. Like for the keyword here is backward curriculum design. So start at the learning goals and work your way back towards the topics, not start with the topics, which is, I think, the most natural thing for us to do as experts. And then we have an independent arts team as well, with a similar idea of there are one or two things that they're thinking of doing independently, like, for example, producing some videos, documentary videos of like a day in the life of a quantum scientist or something like that to help with recruiting and outreach. But they're also embedding or communicating with the individual course development teams as well, because I think there are approaches to pedagogy facilitated by the arts that we could take good advantage of. So one initial idea that I can mention, just because I think this is one of the areas we've made some progress. Coming back to the video, I will throw myself under the bus in terms of age. Like, video production is not a natural thing for me to think about. Like, I'm imagining camera crews and lots of hassle. But to the students, coming out of high school and going into college, they're putting videos of themselves online all the time, right? So you can imagine an assessment modality that, say, at the beginning of the semester, asks students, make a 1 or 2 minute, 5-minute video of yourself answering the following questions. And you can prompt them with, like, what is quantum information? Why are you interested in quantum information? What careers do you see for yourself in quantum information? Do that at the beginning and end of the class. And I think in letting them see their videos, other people's videos, that's a really potentially powerful way to communicate a lot of the broader concepts about quantum information, and do the kind of synthesis that we know as practicing scientists is essential to learning, but we don't really, at least in the US programs, and certainly in OSU's curriculum, we don't really have that embedded in the coursework. It's more focused on this topic, this topic, this topic, this topic. So that's a modality that's very arts focused. It's making a video, and I don't know anything about like how to assess a video or whatnot, but people from the arts world do this all the time, right? There's whole schools of film studies and whatnot, and so that's kind of the aspect of integration with the arts that I think is most near term in terms of what we're looking at.
Okay. Thank you, Zeke. I know we have taken a lot of your time. I mean, it's been a long talk, and with the question answers. And well, so yes, as MSR was saying, maybe